Okay, so yeah, this will be about ordinary differential equations. Okay. So as I told you, like DE, which is like a differential equation, can have a single like independent variable. Okay, a single independent variable. Like suppose y is just a function of x, and it can have more than one independent variable. Okay. So more than one independent variable. That will be the next part. All right. So like how you will know like an like a ordinary differential equation is of nth order. Okay. So say this function phi. Okay. This is a function of x, y. Y is also a function of x, dy by dx and so on, d2y by dx also, dx2, so on till you have the nth order of y derivative. Okay. This function is 0. So in your equation, you will have, what is the highest order you will have? N. Isn't it? So then this is known as an nth order ODE. Okay. Right. So I thought of just giving you a basic background, just a warm up on differential equations before going to the methods. All right. So as you know, solutions of ODEs are functions. Solutions of ODE are just functions, and you have a uniqueness theorem. It can't be always unique. Okay. So just as an example, like you can see just a derivative dy by dx equals to 0.2 xy. Okay. So can you try to find the equation of this? So just by looking at this seems like a difficult problem, right? Just by looking at it. But when I write the solution and you approach it, look in a different way, it will become obvious that yes, this is the solution. Okay. So the solution to this is, yeah. So see this guy, like y equals to e to the power exponential 0.1 x square. All right. So when you take the derivative of an exponential is again an exponential. Okay. So you can take the benefit that 0.2 something y is there in your differentiation on the right side. So this should give you an idea that the form of the function should be a kind of exponential. Okay. Because dy by dx is again equal to something. Okay. And if y is coming, then it must be of a form of an exponential function. All right. But that's not it. Okay. When you integrate it, you will get an integration constant. You know, there will be like infinitely many solutions. Value of c, isn't it? Whatever different values c equal to 0.1, 0.2, 1, minus 1, whatever you take, you will get different values of y. So you will have infinitely many solutions. Okay. But if you set an initial condition, then your solution will be unique. Now, if you set your initial condition to a given, that becomes an initial value problem. Okay. If you give an initial condition to this, to the above problem, or to the above ODE, IVP. What is IVP? Initial value problem. Okay. Great. So uniqueness. So what we saw, what we just saw, what we learned that uniqueness is provided by the initial conditions. Okay. If you give an choosing one of the solution, all right, else it will be just C and it can have infinitely many solutions. Okay. So if you say y at 0 equal to 1, okay, then you put x equals to 0 and you solve for C. Then it will be just one equation and one solution. Okay. So not only the initial conditions, there are something known as boundary conditions as well. Okay. So initial condition is just like for a single variable. Now, if you have more than one variable, okay, suppose you have a function u, which is a function of both x and y, then like you will have this partial derivative and all those. Okay. Like in those cases, you need a boundary condition. That means what is the condition, like what is the starting point of x and what is the starting point of y? Those are like the boundary conditions. Okay. Because x surface to you, okay, then it becomes a boundary. Okay. It now if you see for the dy by dx equals to 0.2 xy, it is just varying with respect to one variable. So you have an interval. But when you have two variables, okay, it becomes like a domain. Okay, therefore you have a boundary condition to it. And if you specify a boundary condition in your problem, that becomes BVP. Okay, boundary value problem. Okay. So first we will learn this one, IVP. Then we will learn a bit about boundary value problems. Okay. Just a tiny bit. Okay. All right. Yeah. So there is something also known as separable ODEs. How many of you are aware of this separable ODE? Separable ODEs. Yeah. Separable ODE. Yeah. All right. So let me recollect. The idea is to recollect the things. So write this function. All right. So can you see that it is indeed separable? Why it is separable? So if you see, like you can bring this y square in the denominator and just the x plus 1 e to the power minus x on the right hand side. So if you see, the left hand side is just involving y and the right hand side just involves x. Now what you will do? Just integrate. Okay. All right. Now you can get easily y. So this is the whole idea. Like if you solve it, I think, yeah, you can easily see that there will be an term. Check that the solution will be like, okay, again C, because I have not yet specified an initial condition. Okay, so I have to write C. If you specify an initial condition, you can solve for C and you will get a unique solution. Okay. All right. There is something also known as exact ordinary differential equations. How many of you are aware of exact ordinary differential equations? Yeah. So yeah, the idea is it's not so trivial phenomenon. Okay, it's not so trivial. Okay, but it has happened that way. Okay, so the idea is you have two functions, m of xy dx plus n of xy dy equals to 0. Okay, now this differential. Okay, this differential equation is exact when there is a condition. Yeah, anyone? All right, so it is exact when you have this condition, right? So this exact you have to recollect, okay? Just read again. So the best place I could find to the basic and explanation where I could find the exact is NCERT. It's really nicely given there. So just check your NCERT book. It's also available in PDF. 12th, okay? Okay, so these are just of the, some of the recap. How about integrating factor? Integrating factor. Suppose your equation is not exact. Okay, why we want to do? See, why we are even learning about exact equations. Okay, exact differential equations. Learning about exact differential equation because it will give us in a form such that it is easily solvable. Okay, if your equation is not exact, you can write in such a nice form. Okay, m dx plus n dy. You can't write that in that form. So therefore, if your equation, differential equation is not exact, okay, you can make it exact, okay, by computing its integrating factor, okay. So that part is also nicely mentioned, okay. So those integrating factor in by what I mean is dy by dx plus py equals, okay. Then you find the integrating factor as I think if is equal to e to the power integral p dx, okay. Then you multiply the integrating factor with y, okay, to make it exact, okay. So those are the basic things. Just try to recollect those things, okay. So maybe this will be one of the problems, maybe as an assignment next class. Try to solve this, okay. Here I am giving an initial condition to you, y at x equals to 0 equals to 1, okay. So try solving using the integration factor. This is the assignment for the next class, okay. All right. Okay. Yeah. Okay, okay. So let us start with the Euler method. Okay. So this is one of the numerical method and to solve the ordinary differential equation and specifically an initial value problem. Okay. So let me start. So I'll just tell you the method first. So we have this initial value problem dy by dx equals to f and then y of x. Okay. So here just we will apply the finite discretization. Okay. So we did this in the differentiation, right? Forward finite difference, backward finite difference. Okay. So the idea will be to create a difference equation, okay, from the ODE, okay, a difference equation. How we will do that? Order, like forward finite difference. Okay, what is yi plus 1 minus yi, right? Yeah. Then before that, I forgot. We will discuss data. Okay, equally spaced x data. That means xi plus 1 as usual in your differentiation, right? That is the difference in between them is h. Okay. Yeah. So therefore by h, right? Am I correct? This is just the forward difference method, isn't it? Yi plus 1 minus yi by h. Yeah. And you just have f of xi, y of xi. Okay. But I am missing also something here. What I am missing? A good thing to write. The first time I am like, devising this method for you. So yeah, this is an order h error, right? Now you see, why our aim is to find yi plus 1, isn't it? Given yi, as I told. So yi plus 1 equals to yi plus h times f of xi yi plus order of yeah. Yes. Okay. Okay. Just see that this h is getting multiplied. So it should be h square. The denominator there is an h. This h is moving on to the right side. The denominator is multiplied onto that. Therefore, how you got this h in front of f? H is getting multiplied from the denominator, right? So this is known as the explicit Euler method. Okay, why it is explicit? Because you want to compute yi plus 1, and that is solely depending everything on the previous state. By previous state, I mean xi and yi's. Okay, if suppose you will see this right hand side depends on I plus 1 data, okay, then it is no longer explicit. It will be implicit scheme. Okay, you are trying to find yi plus 1 on the left, but your right hand side is also involving yi plus 1. Okay, so therefore it is not. So therefore, as you can see, every iteration, the more you iterate your method again and again for different values of I, your error h is getting added again and again, isn't it? Because it is multiplied by h. Okay. So therefore, Euler method is very sensitive to your step size h. Okay, the grid size. So therefore, in order to get a very accurate solution, you have to keep your step size very low in this method. Okay. Error can be controlled by using another form or variant of an Euler method known as implicit Euler method. Okay. So what is that implicit Euler method? So I'll write it here. So y prime, which is f of x comma y, already seen, can be approximated at this point, xi plus 1 comma yi plus 1. Okay. It's simple. Again, the same forward method. It is uniformly uniform grid, so h is there. But here on the right hand side, you will no longer have xi yi. You will have xi plus 1, yi plus 1. Okay. Then can you see what is happening here? Can you observe what is happening here? Finally, you will have yi plus 1 in terms of xi plus 1, yi plus 1. Okay. So therefore, this is an implicit method. Yeah. Therefore, this is an implicit method. Yeah. So what will be this? Yi plus h of? Yeah. Now the question is how we will solve this. How we will solve this? See, this equation is pretty easy, right? Pretty easy to understand and compute, but non-trivial. Okay, you just can't easily interpret this equation. Okay, how to solve this? We will see a different method. Okay. So before that, I just want to give you a graphical interpretation. Okay, of the Euler method. Here I can draw it. So here you have y and x, and this is suppose your analytical equation. Okay. A better one. So you want to find, you have this information. Suppose xi corresponding is yi. Okay. Say yi, right? Yeah. Now you are interested to find this point. You at this point. Okay. That's your aim, right? To find. So this is suppose xi plus 1, and the same is yi plus 1, right? Exactly doing. You are taking a tangent at the point xi yi. You are taking a tangent. Okay. How the tangent looks? Okay, something like this. So my graph is a bit poor. It should have touched here. Okay. But you can easily see that this is the error. This guy here is the error. Isn't it? You are actually, the analytical condition is here, analytical result, but you are actually getting the point below that. You can easily see the gap in the y, okay, due to which the error is creeping in. Yeah, so you can already know that this is not the exact solution. It's just an approximate. Now, what is this? Is a tangent. Then what is this tangent? It's the derivative. right? But still, can you write in a slope form? If you write in a slope form, you will come to this formula again. Okay, that's the geometric interpretation of the forward Euler method. You have 2 points, and I'm asking you to find the slope. Yi plus 1 minus yi by xi plus 1 minus xi equals to xi plus 1 minus xi is h, which is in the denominator. Okay, so you can easily see that this formula is coming up. So that is the graphical interpretation of the Euler method. Okay, just using the slope. All right. Before that, I think we can do a problem, right? So suppose a problem, then we will go to a bit of Python. Okay. So this is everyone ready with your calculator. Okay. So find the approximate value of y. Okay, approximate value of y corresponding to x equals to 1. Even our ODE is given as follows: dy by dx equals to x plus y. Yeah. So you know what to do. What you have to do. So I will just tell you the brief sketch how to do this. Okay. So since h equal to 0.1, okay, h equals to 0, so you have to divide your 2. First. Don't just start computing. Think first what you have to do, then start doing it, because it's just an iterative process again and again. So think what you have to do first, given this problem. See, the initial value is being given to you. At x equals to 0, what is the value of y? 1. And what is your job? Job is to find the value of y at x equal to 1, isn't it? So value of y at x equal to 0 is being given to you. Now you have to find the value at x equal to 1. This point is, and h is being given to you 0.1. So now you have to apply the Euler method till you reach 1. Got it? Iteratively, yi plus 1 equals to yi plus h of f of xi yi. What is f here? X plus y. Right hand side of the differential equation. Okay. So just first step, y naught is being given to you 1, right? When x not equal to 1, can you find y1? What is y1 is y at 0.1. Yes, that is equal to y at yi plus 1 equal to yi. The previous step is 0, right? Y at 0 plus h into f of xi yi. What is xi? 0. What is yi? 1. Yeah, so you can get y at 0.1. Suppose you have got y at 0.1. Then what you will do? Compute y at 0.2. Isn't it? What is that? Y at 0.1. This value already 1. Is it? Plus h of f of xi. What is xi? The previous step. 0.1. Isn't it? Yeah. Then y of 0.1. Is it? Any issues? Sorry. Okay. So y not equals to 1 when x not equal to 0. Yeah. So can you see that we are slowly advancing to increasing value of x? We are predicting the value of y at different values of x. We are marching ahead, right? Same, you have to find till y of 1. What is that? Being done. What I would advise you, just an advice, you can do as you like. You can create three columns, xi, yi, okay? Then what you need? The function f, right? Which is xi plus yi, right? Yi plus 1. So if you just write these values, you can easily compute this one. Will you reach? Will you reach what? So Python also you can solve ODEs, all right? Mostly like the initial value problems. Okay. So there are many different packages, like we will see around 2 or 3, and one of them will be a project. Okay. So as you can see, there is the scipy.integrate.ode int. Okay. And there is also known as something known as Gecko. How many have heard Gecko? You will see this very often, like maybe if you like, I will try my best to cover optimization in this course. Okay. So you will see in optimization, some of the optimization codes get. So this is one of your projects. Okay. You will solve an ODE using the package Gecko. Okay. So, but here in this class, we will talk about two, the ODE int and solve IBP. Okay. These are two packages. Okay. Which you need to import. So ODE int, first we'll talk. ODE int is a function which receives a vector containing the RHS of the ODE system. What is the RHS? RHS is like the function, the form of the function. So it will be a lambda function kind of. And also the vector of initial conditions. All right. It might be that your function is just depending on one variable. So the vector is just 1 cross 1. It might be that you have two different initial conditions like both x and y. It might depend on that. It might be a coupled ODE. Okay. So in that case, you need a vector of initial conditions. Okay. And the time span. All right. Like which time you want to span. So you can see this function df by dx equals to cos x. X belongs to 0 to pi. Okay. So the time span is 0 to pi. X is the independent variable is varying in between 0 to pi. Okay. So you have to specify that span as an argument in the function. What it returns, the output will be a solution. Okay, basically like it will return you the whole data and it's up to you to plot it. Okay, so we'll go to the Colab page. All right, so here you can see this ODE function. We are basically trying to solve the second question. Okay, sorry, x is belongs to 0 to 20. I rubbed it off. Belongs to 0 to 20. All right. So you can see input numpy is np and scipy.integrate. You are importing ODE int. All right. And you're defining f as a lambda function of x and t. is written on the board. Yes. So we want to solve this differential equation. Okay. So d minus 3x square, x is varying in between 0 to 20. So how the function f looks. So we will solve this not using Euler method or anything, but using ODE int. Okay. So as you can see, I'm defining f. First step is to define f. All right. Then I'm saying the time span. T equals to np dot linspace 20. Here, I have taken 401 steps. Up to you, you can take 1000, but yeah, it will be time consuming. All right. So up to you. 100 also you can take, whatever. Till now it is okay. Yes. The starting value x naught is 0.1. All right. So then I'm using this ODE int function. Okay. As in the theory I have told, it will take the function as an argument, the vector of initial condition as argument, which is x naught, and the time span t, which is a length space, 0 to 20, 401 steps. All right. Then the output will be stored in x. Yes. So again, I'm importing for the plot, pyplot as PLT. All right. These are just like the, what you call, like result into form of like a plot. Okay. So you can see I am saying the fixed size is 10, 10, and it is plotting t, x. Okay. So the x is the output. T is already, you know, t is what? T is in between 0 to 20. Okay. So x is the output, which is from the ODE int. Okay. That will be stored in your x data. All right. So the points, the curve, whatever you will see will be in orange. Orange, yeah. So, and the width is 2. If you make the width smaller, you will see the width bigger, the thicker lines. Okay. Grid, yeah, I wanted grid. So plt.grid equals to true. Okay. In bracket, I have written true. So you will see the grids on your plot in the figure. And what I am denoting the x and y labels. So plt.x label is t. So you will see the font weight is bold. If I have not given the font weight, it will be just a normal x. Okay. plt.y label is xt, which is the output. Okay. And these are the x ticks. You should not worry about this. Just I have written like that. plt.x ticks means like your ticks will be only visible in the interval of 2. 0, 2, 4, 6, 8 till 20. All right. Ticks you will see. Similarly, you will have the y ticks. All right. So due to this ticks and all, I am getting some like data over here. No need to worry about the data. Okay. So can you see this plot? Yes. So this is the output of that function which you are seeing here. Okay. If you wish, you can solve it analytically. But yeah, this is a complicated equation, differential equation. So you can solve it numerically using Python. And how also it looks, you can see it. Okay. So this is one of the ODE int function you can easily use. Nothing you have to do. Just use ODE int, give the function, give the initial condition, give the time span over which but what method? So since it is solving a differential equation, it must be using some numerical methods, right? We will see what numerical method it is using inside the Python. Okay. All right. Let me show. Apart from ODE, there is something known as solve IVP. Okay, solve initial value problem. All right, that's also another function. Now it's up to you which one to use. You can use solve IVP or ODE int. It's up to you. But the way it takes the input arguments are a bit different. Okay, ODE int, you will see a bit of different argument set it needs, and solve IVP, it needs a bit of different arguments. Okay, we'll see. Well, here a bit of differences. What is like the difference between solve IVP and ODE int? So you can see both solve IVP and ODE int are functions provided by Python libraries, scipy.integrate. Okay. Next, I will show you an example of solve IVP. In that also, you will do the same thing. SciPy.integrate dot solve IVP. Okay, you will import that function. So yeah, so key differences. One is the input arguments. All right. So solve IPP, like let us go to ODE first. As you know, it requires the user to provide the derivative function, the right hand side of the ODE, right? Yes, clear? That's the first argument. And the initial, all right. So this just I have written an array of time points where the solution is desired. All right. So you were desiring the output in between 0 and 20. Okay. So this is your time step. All right. So if you see solve IVP, whereas solve IVP requires the user to specify derivative function, okay, initial conditions, okay, and the time interval same, okay, over which to solve the ODE. So almost the same. No difference yet. See a bit of difference now in the integration methods. Okay. So if while solving the ODE, you are actually integrating. It's a derivative of y. So in order to find y, you have to integrate, right? So these Euler method and all are like, those are integrating methods only. Solve IVP, like provides several integration methods. One is the explicit RK method, implicit RK, and BDF, the backward differentiation formula. Okay. BDF is not an um, like a first order method. It's a bit different as compared to other methods. Okay. BDF and Adam Bashforth, these are the methods. These are the methods. So, so as I told, the solve IVP and ODE are like very efficient methods, okay, where you can easily solve the ordinary differential equations. All right. So in what way they differ? They differ in the methods. As I told you, you can use forward Euler method, explicit like RK4 method and all. But during the beginning of the class, I told you that these are not the only methods. There are some other, there are situations where these methods will fail. And those systems are known as stiff systems. Okay, I will give a very nice example now. So in order to accommodate that, they are using this backward differentiation formula, okay, and other methods. So as you can see, the ODE uses LSODA, okay, Livermore solver for ordinary differential equations. Okay, they're like powerful methods. These are very recently developed and just for stiff systems. Okay. So yeah, with stiff or non-stiff systems, it is based on, like as I told in the beginning of the class, Adams Bashforth, okay, for non-stiff, and BDF for stiff. Okay, so BDF is a method, backward difference formula, which is usually used for stiff systems. Okay, and the output format, like what's the output format? The ODE we just saw is returns an array containing the solution at all the time points specified in the input time array. In between 0 to 20 here, and you have defined the step size around 401 points. All right. Yes, around 401 points you have defined. So at each of those points, what is the value of y? It will compute and it will give you as an array. That's what ODE will do. Okay. Solve IVP, it returns an object that contains the solution at a specific point, which you'll see, as well as additional information. This is a bit of difference, like what are the success status, like what is the integration time it took, and all those informations. All right. So yeah, same. ODE int is the initial condition to be provided as a single array. You saw we gave as a single array. Like in our case, what was the size of the array? Huh? No, the initial condition was just one. Yes, just 1 cross 1 vector. Okay, but lot of other systems, it will be an array. Okay. So as you can see, solve IVP is also the same. Initial conditions is an array. Error handling, like solve IVP provides a bit more information about the integration process, like including the error estimation and all this. ODE int may not provide as much error detailed information as solve IVP. Okay. So usually solve IVP is good in this sense, because sometimes you want to solve an ODE and you just don't want the output. Okay, you just want to see if the output that you are getting is actually finishing in what time. Can you actually solve it with more efficient and less time? Okay, because it might be a system of ODEs. Okay, after this ODE, it has to do again a bit of long job to do. Okay, so you have to know the time frame. Okay, if you don't worry about the time constraint and all, then yeah, you can use any. So it's actually the user's preference and specific requirements of the problem. Okay, so as we see, solve IVP is actually generally recommended due to its flexibility. All right, so we have not seen yet an application of solve IVP. We will see it now. All right. As you see, we are trying to solve the first question. Okay, on the equals to cos x. Do you know what's the output already? What is f? It's f. What is f? Like if df by dx equals to cos x, what is f? What is f? Are you sure? What is the derivative of sin x? So what will be the answer then? If you have the derivative as cos x, then you are differentiating. What will be that sin, right? d by dx of sin x is cos x. Yes? X. We already know. Okay. But we will solve this easy problem using solve IVP. Okay. Just to see. So as you can see, again the same things. You're taking that from scipy dot integrate. Okay, scipy dot integrate import solve IVP. All right. Then you're defining the lambda function np dot cos of t. Okay, the right hand side of the dy by dx. Dy by dt, sorry. Then t eval, which will be the input argument, the time span. What's that? 0 to n pi. 0 to pi. 0 to pi. Okay. We're solving in between 0 to pi. Right, in steps of 0.1. So solve IVP, here you're using that function. Same as ODE int. Okay. Are you seeing the common things? Yes. So solve IVP, then f is the right side of the function. Then your time span. Okay. Then 0 is the initial condition. Okay. Okay. And t eval equals to t eval. What is t eval? T eval is your span. All right. After that, you will just get your output. Okay. So it's just you have to import that ODE in or import f eval, like sorry, solve IVP, and put your required input to them. That is what is the initial condition, what is the function, what is the time span. All right. And that's it. Okay. Again, these are the beautification of the plots. Okay. Nothing more. So I am doing the subplot here. Okay. Plot plt dot figure fig size. So 12 is your width, 4 is your height. All right. So I'm specifying the width and height of my plots. Okay. I am creating a subplot. Okay. So plt dot subplot 1 to 1. What does it mean? It means 1 row, 2 columns, and I am considering the first element of the plot. Understood? Yes. So the next line, plt dot plot sol dot t. So sol, the variable sol stores the output, like the solution of the ODE, which is the solve IVP, right? Sol equals to solve IVP of that function, the arguments. So sol will contain all of our output. So if you want to access sol dot t, will be like the time like 0 to pi. All right. Sol dot y bracket 0 is the output solution, that is like sin x, which you will see. So you're plotting x comma y indirectly. Okay. But you are referencing it via the sol, because sol has the time span as well as the solution. So if you want to reference to the time step, you have to write sol dot t. If you want to refer to the solution, you have to refer to sol.y0. Yes? Clear? Yeah. So, yes. So 1 to 2, let's come to the next step. 1 to 2 means one row, two columns, but the second element. Okay. So it will be just side by side plots. All right. So what you are doing here, you are just giving the x-axis the same, sol.t, but the y-axis is a bit different. How it is different? We are computing the error here. Sol.y0 is the numerical solution. All right. But np.sine of that time is the analytical solution. We already know that the solution is sine. And we are comparing what's the error of this solve IBP function. Okay. Is it doing, fine, or is it showing a lot of errors? How we can do approximate minus analytical or analytical minus approximate, up to you. So this is the output you will get. Okay. So yes. So as you can see, this is the sine function from 0 to pi, isn't it? Matches. At 0, it is 0. At pi, it is 0. At somewhere pi by 2, which is like 1 point something, it is 1. So okay, we are okay. So it is kind of predicting the sine function. Okay. Now, what you will do? Now, on the right side, what we are showing? Error. Error in the sense that difference between the analytical and the approximate. Analytical is already signed. We already saw. Numerical is what you saw on the left side. So this is the error. You can see it's in the order of around 0.0015, which is quite good. It's predicting quite good, I think. Yeah, if it is 0.1, it is bad. If it's 0.01, it is okay. 0.001, it is nice. Okay. So this right hand side is just the error. It's quite interesting to see that it is decreasing and then increasing. Interesting to think why it happens. Okay, but why like the error is going okay for a short time like that, then dipping and then again increasing. Okay. So S0 equals to -1. That's the y value. Okay, here y is like S. Okay, so if you are seeing S, that's the y value. Okay, so S0 equal to -1 is the initial condition. All right, at 0. So we are applying the explicit Euler method. So S I have defined already as zeros of length T. What is T? It is this array. So size of this array. So T and S should have the same size, right? Because T is the input and S is for every input you should have an output. So length of okay, and S of 0 is S0, which is the initial condition I have set. Okay. So you can see easily that this is your. So for I in range 0 to length T minus 1, which you have done on paper, you calculated 0, then 0.1, 0.2, so on, you went till 1. Is it? Yes. For the previous example, when you did on paper. So that same thing we are avoiding by using a for loop. We will do the for loop. So Si plus 1 equals to S of I plus H into the function, the ODE, F of Ti and Si. On the right side, all you can see ith state variables. And you are predicting the I plus 1 step. Then it is done. After you have this S data set, you can easily plot them now, right? So this is now the beautification of the plots, okay? Which is a good practice, actually, okay? So how PH is again 12,8. All right, you can try to experiment with the fixed sizes. All right, maybe you can give 8,12 instead of 12,8. See how it looks. Play with that numbers. Okay? PLT.plot T, S. T is our time, S is our Y variable, right? So you can plot T, S. And how I am plotting it? In red, but with dotted lines. Sorry, not dotted lines, with dashes. Okay. label it as approximate. Okay, so it will create a legend over in your plot, giving the dash red lines and saying that it is an approximate. Okay, so you all in one line you are getting ELT dot plot t comma minus np e to a minus t. What will be the solution? It will be the solution minus e to a minus t. Okay, so that I have given as blue. All right, and I have written it as exact or analytical solution. Yeah, exact or analytical solution. Then the title of my plot is approximate and exact solution, because we are showing both exact and analytical solution, right? Approximate and analytical solution. Yes. So then the x and y label I have given here t and f of t. I want grid, yes, plt dot grid. Then it will show these grids in your plot. Okay. Then where I want to position my legend. Where I want to position my legend is a good practice. Usually put a legend after you see the plot, because then you can see some free spaces in your plots. Okay. So as you can see, lower right. I have given the term as lower right, right? Here, lower right. That therefore it has come down. You can try other where you want to position it. It can be top left, top right. Okay. PLT.show. So this is the output you actually get. Okay. So as you can see, the x-axis is the time step t, and the y-axis is our solution to that ODE. The blue one is the exact solution, and the dashed red are the approximate solution via explicit Euler method. All right. So as you can see, when we are near the initial value, our analytical and approximate solution are very close to one another. But as we move ahead, like increase our x value, they are separating from one another. Is it? Like you can see how. So therefore the error is coming. The error is creeping in, right? One of your project would be to solve ODEs using Gecko. Okay. So Gecko is like, I have missed this. So let me tell you just a brief outline, but you have to do like as I described using solve IVP and ODE int, you have to do something using Gecko. Okay, that's your project. Okay, one of the projects. So Gecko, just a bit of outline. Gecko is a comprehensive Python optimization suite. Okay, so basically used a lot for optimization, which I plan to show. Okay, then the primary purpose is to tackle any dynamic optimization challenges. Gecko is adept at handling mixed integer, nonlinear differential algebraic equations. Okay, nonlinear optimization problems. Of this. Initialize a Gecko model M in Python. The following you're seeing this line number 1. You don't have to type 1. Line number 1, line number 2. So from Gecko import Gecko. Okay, and like model. So M equals to Gecko. Remote equals to false. What does it mean? Remote equals to false. So assigning false value to the parameter remote informs Gecko to set the server to the local machine. Okay, it will be just your laptop machine. Okay, not your cloud. All right. So if the model M contains a variable x that is bounded from below by x min and from above by x max and has the initial value x naught, then it can be declared as follows. Yes, so M has lot of attributes. You can access the attribute variable. There are other attributes of Gecko model M. You are trying to access the attribute variable of Gecko. Therefore, you can do that by using m.var. All right. You can show the value, the initial value, which is x naught, the lower bound, which is x min, the upper bound ub, which is x max. Okay. So this is the information I provided. Now, up to you to do the project. Okay. So one of the group will have to do this Gecko project. Okay. So we talked about Euler method. So next we move to the Ranjikutta. Okay. So as you can see, Ranjikutta method is actually one of the generalized method. And as we progress now, you will see that variant of Ranjikutta method. Okay. So Ranjikutta is actually the generalized method, but Euler method is one of the variant of Ranjikutta method. So another variant of Ranjikutta method before going to actual Ranjikutta is the Hume's method. Okay. Try to approach this from the Euler method, the explicit Euler method. So what we have the differential equation y dash equals to f of x comma y, right? So the idea for the Hume's method is to predict using Euler and then correct it. So this is like a predictor corrector method, okay? So the idea is to predict using Euler, then you correct it. So just writing. So in order to find that y, we have to integrate both sides, right? So integral y dx, dy by dx. And I want to integrate it from xi to xi plus 1. Okay. Now the trick I will apply is on the right hand side, you can see the integration, right? Xi to xi plus 1, f of xy dx, right? So that integration, we can approximate it via using any of the integration methods. What integration method we learned? Simpson's 1/3, Simpson's 3/8. Okay. But we also learned another one, that is a trapezoidal. Okay. We will use that here. Okay. So we have 2 points, xi and xi plus 1. So we'll apply the trapezoidal rule here. Okay. So how it will be? It will look like. So since you already know that this is a uniform grid, that means xi plus 1 minus xi and all those are same. So that is like h. Okay. So this will be like h by 2. You also know this from the trapezoidal. Then what I should write next? Tell me. F at those 2 points. The value of f at those 2 points, right? Yes. That's like an area of trapezoid, right? The x length versus times the sum of 2 y length. The sum of 2 y length will be f of xi yi plus f of but the main problem is here it will be yi plus 1 minus yi, right? Yes. So now the yi plus 1 equals to yi plus h over 2 xi comma yi plus f of xi plus 1 comma yi plus 1, right? Now again we came to this method where you are trying to predict yi plus 1, but actually inside that you already have yi plus 1. Okay. So yes. So this is an unknown quantity. This is an unknown quantity, right? What we shall do next? You suggest? Can you suggest what we shall do next? So since we don't know the value of yi plus 1, value of yi plus 1, we can predict. We can predict the value of yi plus 1. And how we can predict it? We can predict. So what I can say is predict the value of yi plus 1 as predict yi plus 1 as something like yi plus 1 star, and this yi plus 1 star is the forward Euler, okay, which will look like yi plus h times f of xi yi, right? Is it okay? Shall I write in place of this? Waiting for you. Y plus 1 equals to yi plus h, like maybe h by 2 k1 plus k2. K1 is f of xi yi, k2 is f of xi plus h comma yi plus h f of xi yi. Yes. So you just keep a note on this summation of k1 k2 and all those things. Okay. For this, you will see different values of ki's. Okay. So you can see the method is now still explicit, is it? Now the method is still explicit. Am I correct? Till this step, explicit. But when I incorporated corrector method, this one is explicit. Is it okay? Because yi plus 1 is everything depends on xi yi. Yes. So generally this Hume's method is known as the, so second order RK method. So if you see Euler method could also be written as this way. Okay. And Euler method is known as the first order Ranjit-Kutta method. Okay. It's a way of saying that. So Euler method is the first order Ranjit-Kutta method. Hume's method is the second order Ranjit-Kutta method. And then we will see what is like the third and fourth. So I will write the generalization towards the Ranjit-Kutta method. Okay, so first is the Euler method. It's also known as the first order RK method. Okay, so how we are writing the Euler method? It is like yi plus 1 equals to yi plus h f of xi yi, right? So that I am writing as k1, where k1 is xi yi. Am I correct? Method. Okay. Okay. So how you are writing it? yi plus 1 equals to yi plus, yes, h over 2 k1 plus k2, where k1 you already know. K2 is K2 is you can now see we can generalize this. We can generalize. How we can generalize? So generalizing, write yi plus 1 as like yi plus h times the summation. There will be a lot of multiplication and addition of a, I, and yes, so support me. So see, here I have written as a generalized statement. We know that some K1, K2, K3, and so on. And in front of that, some constant is being multiplied with Ki's, Kj's here, sorry. Some constant is being multiplied with K. So if you see above, h by 2 was getting multiplied with K1 and K. Sure, h by 2. Yes. So in order to, we can't say in the first step you got h. In the first step you got h. Yes. So constants are differing. So therefore I have generalized using Aj, Kj. Okay. Aj times Kj. Okay. So if you see your K1 will be again that f of xi, yi. K2, can you say? So this is just a generalized form I am writing. It might not be trivial. Okay, but bear with me. But I think maybe we will not follow this. Show that you can write K1 and K2. But don't worry about the T1 and Q11. We will resolve that. Okay. It might be complicated. We will not go into that. Unfortunately, in that way. Okay. And most of the SciPy solvers, they internally use this RK methods inbuilt. Okay. Like RK fourth order and all this. So since we have seen the first order RK method and second order RK method, we are now good to actually see the Ranjakutta fourth order method. Okay, which is actually our interest, and it is actually a lot better than the forward Euler which we discussed and you solved in class. Okay. So before going to the Ranjakutta fourth order method, I wanted to show you guys the Ranjakutta first and second order method. Okay. So this is actually the important one. So the Ranjakutta fourth order method, and we'll solve using Python and by hand. Okay. And that's it for the class. So again, you have like your differential equation, y prime is f of x comma y. Okay. Ranjakutta method is given as follows. Yi plus 1 equals to yi. Okay. Then plus h times the summation aj kj equals to sorry, the j equals to 1 to 4. Okay. Yes. Now you must be wondering what are these. Once we have this knowledge, it is done. Okay. So this is the definition. K1 is defined as f of xi comma yi. Okay. K2 is defined as f of xi plus p1h comma yi plus yes q11 k1h. Okay. We will what are these q11 and all those constants. Okay. Or maybe like I can take it easy, is it? Or maybe I will just say it later. Just hold on. So you don't need to worry about this difficult looking constants for now. Okay. I will just tell their values very soon, but there is a purpose why I am writing this qij variables. Complicated way. Obviously, this is very complicated. And K4, any guess what I should write next? P3. Just to use a bit of basic common sense. That's it. Then yi plus q31 plus q33, right? K 3h. It's just like how it flows. Okay. But this is looking very complicated, right? Looking complicated. Yes. So our goal is to find those constants like PIs, Q1, 1, Q2, 2, Q3, 3, all those. Okay. So you can find those, okay, using Taylor series, derive it and all those. We are not going to do that. Okay, in this case, no. I'll just show you the the answer for this. Okay. What are these values? So after you solve this, solve and compare. So idea is the same. You will use Taylor series. You will equate equations. Finally, you will get a set of equations. Okay. So you will get a set of equations which you will solve. Okay. So those equations will be like involving P1, 1, and all those. Okay. After you do that, after you solve those simultaneous equations, you will get those values. We are not going to show it, but I'm showing the method to you. Okay. So how it will look? Yes. So after you solve this, you will get this form. So you don't need to worry about all these quantities for now. The real thing begins. Okay. So if you want to use the RK4 method, you have to use this. Yi plus 1 equals to yi plus h over 6 times k1 plus 2k2 plus 2k3 plus k4. Okay. There is an interesting coincidence. Count the number of coefficients 1, 2, 2, and 1. Okay. They add up to 6. And that's what you are dividing it by. Yeah. And what are these k1s? So k1 is like the same yi. Now k2. Note that previously we saw that k2 was depending. Does it? Yes. So here also it will depend. Okay. How? So it will be f of xi plus h by 2, comma yi plus h k1 over 2. Now you see, after you compute k1, then only you can compute k2. You can't compute k2 and then compute k1. Obvious, right? Because k2 is depending on k1. Only after you get the value of k1, you can get k2. Yes. So k3 will be again same, xi plus h by 2, comma yi plus h k2 by 2. Following the trend, how it is evolving, right? We are seeing some similarities. Then k4, xi plus h, this will be a bit different, yi plus h k3. Okay. So let me repeat again. The problem which I want you to do. So using RK4 method, Ranjagutta fourth order method, okay? Find the approximate value of y. The approximate value of y, okay, at x equals to 0.2. All right. Given that, what is given to you? Given that dy by dx equals to x plus y, okay, y equals to 1 when x equals to 0, okay. So x equals to 0 at x equals to 0, y equals to 1, right? And your job is to find what's the value at x equals to 0.2, okay. So I suggest that you just take h equals to 0.2 and start. So at one step you can get your output. Can be louder. Have you heard of this, like A is like a population growth rate in ecology? Yes. Captivity. Okay. Okay. So anyone can solve this equation? ODE. What's the general solution? What's the general solution look like? It should be pretty easy. What's the general solution? Can you see just by just by eyeballing the ordinary differential equation, can you just interpret that there is an exponential term coming in? Eyeballing. See, how I eyeball this equation. Dx by dt equals to a times x. What I will do in my mind, I will bring that x, the denominator, and take what I will get dx by x equals to a dt. Okay. Then what I should do next? I should integrate. Okay. If I integrate x, what I should get? Log of x, natural logarithm of x. That's like at. Okay. Now, if you want to compute x, what you have to do? So it is like x equals to e to the power at. Just by eyeballing this, I solved it. Okay, so it should be like that. If you want to, predict some equations and all. But naturally, it will come with experience. So I will just write that equation here, which I have it with me, x naught e to the power at. Okay, using the IC. Okay, initial condition. But all these equations apart, but what can we get what information are we getting from this equation? What information are we getting? If the population of that organism is starting at x naught, then how it varies with time? Okay, it varies with time as xt equals to x of t equals to x naught e to the power at, right? Now, depending on the parameter a, the population will either like revive or it will cease to exist, right? Is it okay? If a is greater, a is positive, or like maybe if a is positive, what happens to xt in long run? As so if a is greater than 0, then what is the population of that organism x in the long term? Can I say that? Can I say that population keeps on increasing? Yes. Everything is positive, so exponentially it will grow, right? So if a is greater than 0, population increases exponentially. Okay. Now, if a is greater than 0, what you will see? Population is decreasing, like going towards 0 exponentially, right? Exponentially. Okay. So this is not a good population, right? This is not a good population model. Why? Because in real life, you are actually increasing. Okay. Even the insects, they could just like populate and they can increase their environment and the evolution can take anything. So why that doesn't happen in real life also? So that's the but our job is to mathematically model it, the phenomenon, the real life. Okay, so this is not a good real life model. Do you agree? Or is it a good real life model? Because just depending on the parameter a greater than 0, a less than 0, keeps on decreasing. It's not going to a steady value which we want, which is now the case. Okay. So therefore, there is a need for like a new model to take place. Okay. We need a new model. Okay. So therefore, I think an ecologist known as named as Verhulst, he came up with a logistic model. Okay, which is a better model than this. So what he did? So his equation is like this. He interested in all this. So if you see, he came up with this equation. Dx by dt equals to ax times 1 minus x by p. All right. So he said that this model actually see some like steady state. Like actually a population organism can actually, the number of those organisms can actually reach a steady state. Okay. And this we will try to solve using analysis as well as in Python. Okay. So yeah. I will give you this as an exercise, okay, to try it on your side. Solve it analytically. You can easily solve this. Just dx by them. Then you can. So what result you will get is, I'm telling you can double verify it. As your time t tends to infinity, right? In a long time run, your population x, okay, approaching p. A good model because your at least a population is settling to some value instead of just going somewhere or just decreasing continuously. All right. So next class, like maybe one of you can come to the board and solve this. Okay. Maybe right. Not to me remembering. Okay. So what we will see is just by using the Varust model, we'll solve a coding problem now. Okay. So again, the same problem which I told you before, a forest that can sustain a maximum of 10,000 deers. Okay. If the maximum it can sustain is 10,000. Okay. So 10,000 deers it can sustain. Maximum. This is the max. Okay. And the current deer population, currently the deer population is around 2,000. Okay, but maximum it can sustain is 10,000. Okay. So the idea is predict the population variation of the deers, predict population variation of the deers for the next 20 years. Okay. All right. So we will check this via coding for now. Not use this 2000 and 10,000. Okay. We will just use 2, the non-dimensional 2 and 10. Okay. Closer round off. Like 2 means like 2000 and 10 means like 10,000. That's like the scaling we are doing. So using the Varust model, can we predict this? See, you have been given P. Am I right? P is the, I did not tell what is P, but P is the maximum sustainable population. Yes. Yes. So P is like 20. We'll see. So you also know the current deer population also, which is 2,000, and maximum it can sustain is 10,000. Okay. And the time is given to you 20 years. What will happen after 20 years to the deer population? You have to find using the Varust model. Okay. So we will use this Python. This is what I have for that model.